Okay, so we are approaching the middle of the course, because in 25 hours we are at lecture 11, so 11 hours, 10 hours gone. And we come to one of the central subjects of the course, manifold learning. So the manifold hypothesis in data analysis, you could say, postulates that data collected from a given phenomenon are often intrinsically low-dimensional, meaning they depend on a small number of parameters, of features, of hidden variables, even if they live in a high-dimensional, usually Euclidean space. Now, an instance of this phenomenon is what techniques like singular value decomposition or principal components analysis try to grasp. They do that in terms of noticing when your data live close to a linear subspace. Okay? So the one-dimensional instance is the linear regression, where you try and fit your data with a line. With techniques like PCA, SVD, whatever, you try and understand if your data live on like a plane or something like that in many dimensions. Why high-dimensional space? Well, because usually you collect your data in form of, I don't know, images, videos, sounds. So you have a lot of inputs, like all the pixels of an image, all the pixels of every frame of a video, all the sampling points of a sound recording, or worse. I mean, your data could be data on some big population where you can actually you're just looking at one phenomenon, so you think there should be one or two main reasons for this data to vary, but in principle you just have, I don't know, several thousands of coordinates. Examples of this. So the first example is famous. I mean, these are almost all famous examples, meaning not that you know them, but meaning that if you go through the literature and read every paper about these, you will find these examples, because these are the common data set that everyone had. So the written digit 2, meaning that you go from this, which is a Z to me, but to some people is a 2, to something like this maybe, to something like this. So you could, and you collect images which are, I don't know, a number of pixel times a number of pixel, which all represent the digit 2, handwritten by someone. And I mean, they vary. And I mean, you could notice, you could also, I mean, people studied handwriting for a long time before data analysis. You could notice two main reasons of variance, variance in a loose sense, among these images, which is the so something like, okay, let's see if I can make the examples clear. So on one direction, you vary the way you draw the lower arc. On the other direction, you vary the way you draw the upper arc. How bent is the upper arc and how ornate is the lower arc. But I mean, I'm not really good at that, but I hope you can understand that. These are the two main features you would, and obviously, I mean, these images in principle live in a space which is number of pixels times number of pixels, which is usually something of the order of, I don't know, thousands of, tens of thousands, something like that. But in a loose way, you would say that this thing is not really two-dimensional, but is a two-dimensional surface perturbed a bit, with some noise added. Hand movements. Oh, this is also a famous data set. So, like the pictures of a hand moving at various inclination of the wrist, doing things like that. And the basic thing is a given, let's say, the usual thing you do at physics lectures in various positions. Here you have a number of parameters, which is the rotation of the wrist and the rotations of the wrist. If you don't move the fingers, you have just the rotation of the wrist. So in that case, you would like to find like Euler angles or something like that. Head movements, the same, like the frames of a video where a head moves left, right, up and down, and whatever. Now a more practical example, complex molecules. So complex molecules meaning like proteins or stuff like that, where you have a lot of, or organic molecules in general, when you have a lot of atoms stuck together, but they're not just, piled one over the other or amassed, so they form rigid structures. And even if in principle they can have a really high number of configurations, because they do, every link between two atoms could in principle turn around the other and whatever, in fact there are a very limited number of possibilities. And this was actually, the written digit 2, the hand movements, head movements were handcrafted to see if the method worked. This is an example where the people didn't know. They suspected that for theoretical reasons there should only be a limited number of possibilities, but they weren't sure. But they analyzed the data, and it turned out that actually it was like that. By the way, if you find a good method to analyze the data, you won't only recognize the manifold and probably find the dimension of the manifold where your data more or less lie. You could also, in some sense, recover some sort of local coordinates in your manifold, and which, if you're lucky enough, will be meaningful. Like for the digit 2 are the curvature of the upper arc and how ornate is the lower arc. So are features which have a meaning in your data set. So also for this chemical application, they found that the parameters had a meaning inside the data set. I cannot go in depth because I don't know anything about molecules, and other stuff. So the problem is, how do we find the low-dimensional representation of such a manifold? Now, it's easy to, a low-dimensional representation, what does that mean? Because you have some points in Rn. You can always project to a plane. Who cares? You take a random plane and you project over it your data. It's a low-dimensional representation, which probably doesn't preserve any characteristic of your data set. So you would like to preserve some features. Features here it's not the right word, but because feature in this setting means something else usually. But interesting characteristics you would like to preserve with this low-dimensional representation. Neighborhoods of point. being close or being far between your data points. Okay? So the usual problem with the projection is that if you project not transversally, you could project a whole chunk of data on a small set. Distances between points. Also between faraway points. I mean, you could be interested in preserving local distances or even global distances. And we saw that on a manifold, local and global are quite different, because locally there is always a geodesic and things are in a way, but globally it's not so clear. Local geometry of angles. So if two geodesics are perpendicular, meaning that the scalar product of the tangent vector is 0, you would like to go down and somehow have perpendicular directions in your representation. Maybe, I'm not saying that I want every item on this list. This is a list of items that one could like to have separately, each on their own. Riemannian metric. You could say, okay, I want an isometry. I want a low-dimensional representation which is exactly like the original manifold in terms of metrics. So not only distances, not only angles, but both and globally. It's a lot to ask. Covariant derivatives. You maybe want even more, that you can compute derivatives on your low-dimensional representation. Now, usually you don't have a manifold. You have some data points which you think lie on a manifold. But you have just points, a finite number of points. So the first step in almost every of these methods is to build what is called a neighborhood graph. We have n points in Rn, and we believe they belong to submanifold M of dimension k. Okay, structure is not written like that. We would like to organize such points in a data structure that takes the metric into account. So it's a graph which, spoiler, it's a graph whose nodes are the points and whose edges are close by points. So the nodes are the points, and we calculate the distances with respect to the Euclidean metric of the ambient space. Okay? Now we would like to connect the points which are close enough. Why? For this reason. Take a bottleneck, a literal bottleneck. So this is a surface in R3. Now I consider a point here. And a point here. What happens there? Well, it happens that their distance in, if you look, for example, from above, you will see something like a small circle and a point here and a point here. So the distance between the 2 points in the Euclidean space in R3 is smaller than the distance in the manifold, because if you want to stay on the manifold, you have at least to travel on this circle, or maybe to move in some other directions. Now, you can worsen things. I don't know if I can draw it, but think about something like this. A very squeezed ellipse and a cylinder over it. Now, this point and this point, well, their Euclidean distance is just this segment, but their distance on the manifold is probably this curve. Okay? So computing distances in Rn in the ambient space not always is the same as computing distances on the manifold. Actually, almost never the same. So that's why we would like to connect with an edge those points which are close enough one to the other. Close enough because if we look really close to a point, the Euclidean distance is the same as the distance on the manifold, because the manifold is almost locally flat. Okay? For example, take normal coordinates and it's flat to the second order in those coordinates. So if we look at a really small scale, the distances in Rn approximate the distances of the manifold. The problem is how small, obviously, and what exactly does it mean, close points. We have two choices. So we connect all the points such that their distance is less than a given bound. So we compute all the distances between points. And then we only look at a really small scale. So if their distance is smaller than something, we connect those points. If the distance is bigger, who cares? This could end up, if your data has some outliers, this could end up with isolated points, because you could have points which are too far from everything else to be connected. To overcome this difficulty, there is another strategy which is, however, more difficult to implement, which is the KNN algorithm, which connects a point to its nearest neighbors, meaning you order the other points with respect to their distance from your starting point, and you connect the first k points to it. And you do it for every point. Now, you see the problem. You have to order every time all the other points with respect to distance and connect the first k. It's computationally difficult. The other one, it's easier. You're just searching through the metrics and checking if the distance is less than epsilon or not. Now, there are a lot of algorithms to do the second one, even quite efficient ones. So in any case, you have your graph where you connected close enough points. So what you end up with is a sort of net on your manifold. So if it's a surface on R3, you kind of triangulated your manifold. Not really, but somehow you wrote it as a mesh. So you have vertices, you have edges, and if you fill up your polygons, your cycles inside the graph, you have a mesh decomposition of your manifold. Obviously, if you have enough data and if you have a fine enough scale with either epsilon or k, whatever. Once you do that, you have a graph, and you put a weight on each edge with the distance. So the weight is only between edges that are connected. So in the first case, the distance will be, the weight will always be less than epsilon. Now, once you have this neighborhood graph, I mean, sometimes you will just use this graph. Sometimes you will even almost ignore it. Sometimes you will need more. But let's start just using exactly this graph. Now, if you think that that is a good model for your manifold, you could try and embed that graph in some Rn in a way that approximates your distances. So you connected some point and you calculated those distances. The other ones you didn't because you thought that in a bigger scale, the distances in the ambient space didn't reproduce the distances on the manifold, so you ignored them. So you want to represent in low dimensions your graph so that connected points are more or less at those distances, and far away points, not connected points, are far. Now, write down the weights matrix and compute the degree matrix, which is the sum. I mean, this is a symmetric matrix. The degree matrix is a matrix that on the diagonal has the sum of the columns, rows, whatever you want, of the weight matrix. And you compute D minus W. So on the diagonal, W has all zeros because the distance from the jth point to itself is 0. So the weight is 0. You are subtracting, well, just think about W minus D. You are making so that every row has some 0 and every column has some 0. Because you are subtracting on the diagonal the sum of all the other elements on the row or column. It's the same because it's symmetric. Now, if your graph is connected, and if you use the KNN algorithm is connected, this matrix has 1 0 eigenvalue and n-1 positive eigenvalues, which have eigenvectors u0, which is the 0 eigenvector, u1, un. Now, u1, un, the eigenvectors, give you an embedding which sort of respects these conditions. Namely, you go up until a certain k, okay, and you consider the points in Rk which are obtained like that. So xj is the jth coordinate of the first k eigenvectors. This could be a good choice. This sort of works here. Another better option is to normalize every coordinate by the square root of the eigenvalue. I mean, as to why this works is not really a part of the course, because it doesn't have anything to do with the differential geometry. It's actually just linear algebra. And I think I've explained the version of this as the last lecture of a first-year course in linear algebra. So I will put the link on BIP to the lecture, which is in Italian, obviously, where I explain this. It's the weightless case, so where all the weights are 1 or 1 over n, if you want the sum 1. But it's more or less the same. You are trying to minimize a quadratic form, so you end up finding the eigenvectors of the associated symmetry matrix. And this matrix L is called Laplacian of the graph. Now, the only reason why I'm talking about this is because this is the first thing you could try, particularly if you know some discrete mathematics, or some graph theory, better. And this does not work so well. I mean, sometimes it does, but not always. But the point is that from here came many ideas of what we are going to see. I mean, the standard reasoning is to try and reduce yourself to some eigenvector extraction problem, in the same spirit of this. Now we will see 3 examples of manifold learning methods. But first, we would like to complete the distance matrix, because if you think about it, what we did before was to embed our graph just considering the distances between close points. So we set everything else to 0, which meant not connected, so really far away. Now, that's the main theme we started with. The distances on our manifold are approximated by the distance of the ambient, of the big Euclidean space, only in a small neighborhood of a point. This is why we looked only close by to every point. Now, if we want to compute distances on M, we have to travel through the graph from one point to the other and see what the shortest distance is. A very stupid way to do that is the following. You set every distance to either what you found, if you use the distance, or to plus infinity if they're not connected. And then recursively, you replace a distance with the minimum of the sums of the distance and the sum of every, two distances, okay, passing through an intermediate point. You repeat it until you calculated every distance and everything is stable. This is not an efficient way to do that, but there are a lot of algorithms that find minimal paths through graphs. So this can be done in various ways. This is just the starting point, which is really, really long. Don't try it at home if you if you don't want to well, wait quite a bit. I mean, because also usually these graphs are like, I don't know, 100 points at least, 1,000 points. So you are going through the set of all points a number of times. It's not fast. In the end, you obtain a symmetric matrix A with all the distances computed along the graph, so traveling through the graph. Which, if you believe that your data set, your initial data set, was sampled in a good way from your manifold, what you just found is a good approximation of the geodesic distances on your manifold. Now, sometimes you would like not to use exactly the distances, but some function of the distances. For example, the distance is squared, that we will see, or in some cases when you are dealing with probabilistic stuff, a to the minus square distance, or a to the minus square distance over something. So I think you recognize the function. But in any case, many times you start with these, many times. In one of the following algorithms, you will start with this matrix of the distances, which we will call A. So W is the weights, A is the matrix distance. Now the weights will change, but that's a problem for another day. First algorithm we talk about, IsoMap. It's from, I think, 21 years ago. And so IsoMap tries to give a low-dimensional representation preserving all the geodesic distances. So not only preserving the close-by points, but also the geodesic distances between distant points. How? We start with our graph and compute the neighborhood graph. Usually, we compute the K, you use the KNN algorithm, so the K nearest neighbors, because it gives you a connected graph. But in principle, nothing excludes that you could use the epsilon neighborhood system, so just connecting those points which are closer than epsilon. You compute the distance matrix, the matrix A we talked before, and apply multidimensional scaling to the matrix. So what does it mean? I mean, multidimensional scaling is a linear way of reducing dimension. So it's like PCA in some way. So I'm sketching here the standard multidimensional scaling algorithm, in case you never met it. We compute the matrix of square distances, and we do what is called double centering. So this matrix J what it is. Okay, 1 with n is the vector with all ones. So 1 transpose is the matrix with all ones. And you take identity minus 1 over n, this matrix. This procedure, in the end, produces something which has 0 mean on every row and every column. So I'm multiplying on the left and on the right to end up with a symmetric matrix again. Because A was symmetric, was a distance matrix, so the distance between I and J is the distance between J and I. B was symmetric, and also X now is symmetric again. Okay? And then we find the eigenvalues and eigenvectors of X, and we use the same procedure as before to obtain the embedding. So this is somehow similar to the Laplacian, only done on the square distances matrix. Sorry, on the on these matrices, which is actually the matrix of scalar products. But anyway, now, well, why it works? Well, because it's not technically difficult to show that what you are doing here is minimizing a given quadratic expression which represents the matrix B in a way, which relates with the matrix B, so you end up with points whose distances approximate the elements of B, which are the square distances. Now, what you end up with? You end up with n points. Depending on how many eigenvectors you select, you will be in a different dimension, okay? So one parameter is the number of eigenvectors you want, and you get n points, x1, xn, which realize your points p1, pn, which are your data set in Rk, such that the distances approximate in some way dij. Now, how do you decide which k to use? Well, you look at how bad the approximation is. For each k, you look at how bad the approximation is. And when this error drops down dramatically, there is your true dimension of your data set. IsoMap works well with manifolds which are approximable with convex regions of Euclidean space. And obviously, when the number of points goes to infinity. The problem is that the multidimensional scaling is a slow algorithm, so IsoMap is terribly slow. And if you do IsoMap with k equal 2, say, and you want to try k equal 3 to see how much the error drops, you have to do everything from the beginning. So if you want to raise the embedding dimension, you cannot build on what you did before. You have to do everything from the start again. I mean, the algorithm part, the graph and the distances are the same, but the multidimensional scaling. So it's quite slow and expensive too. And also, if you use k and n, you end up with a connected graph, so you don't have problems like having what's the problem here with not connected graphs? The zero eigenvalue, probably. But with k and n, I mean, if you have an outlier, you will connect it to something. So you will end up with really high distances from that point to the other points with respect to all the other distances. So if you have an outlier on your data set, IsoMap gets really, really, really scared about that, and it perturbs a lot the results. So usually you remove the outliers before performing the algorithm. Now, second algorithm, locally linear embedding. Locally linear embedding tries to approximate locally your manifold with flat pieces of Rn. How you do that? Well, if you're in Rn and you have enough points, every point is a combination of the points nearby. On a manifold, this is not true. I mean, take a sphere. No, you can have multiple connected components, but you cannot have just one isolated point, which is what troubles you usually. If you have multiple connected components, you can isolate each component. The problem is that you have one isolated point, which doesn't fit well in the algorithm. That's the whole thing. But if your dataset separates into two different pieces, okay. I mean, you will analyze both pieces because they are intrinsically separate in some sense. I mean, it stands to reason that you could restrict your analysis to one part or to the other part. In the other case, but that's not an outlier. I mean, it's not one point really far from the others. These are just two parts. And anyway, I was saying, local linear embedding. We try to flatten out the manifold. So we try to write every point as a combination of the nearby points. How does this work? Well, obviously it doesn't work well on a big scale. Think about a sphere, take points on the equator. You cannot write the pole as a linear combination of points on the equator. But if you look close enough to one point, the nearby points will help you reconstruct it. So you do the wrong thing. I mean, you do this. You compute the neighborhood graph, and you try to write every point as a combination of nearby points. Such that the sum is 1 and the coefficient is 0 if they're not neighbors, so if they're not connected. Now, notice that I'm not imposing that the weights are positive, so you could have negative weights. It's not a convex combination, it's a linear combination. Now, you take these weights and you try to find lower dimensional points which minimize the same function. So you try to find lower dimensional points which are the same relation, each with its neighbors. And you want them such that their mean is 0 and they are they respect this relation. Now this comes out automatically from the optimization procedure, but anyway. Now, why I told you that it's the wrong thing? Because the reasonable thing to do would be to guess the points x, find the weights that minimize this function for the projected points, and see how much error do we get up here. So we decide the weights in the high dimensional space, and then we try and find projections which more or less respect those weights, those linear combinations. The ideal thing would be to find points, guess points in the low dimensional space. Write every point as a combination of their neighbors, which is easier down there, and then apply the weights to the original points and see how much we get it wrong. And then try and optimize this function. The problem is that this is terrible to optimize. It is really, really hard to optimize this. This workflow is much better, but it's less optimal. Anyway, these two optimizations seem hard, but they're not. Why? The optimization problem in step 2, so finding the weights, in principle could explode because the weights could be positive or negative, and you just have a linear condition on them. But you have a closed form solution, so you can write down the solution in terms of gram matrices. You can write everything down, so it's easy. And the optimization problem in step 3 is solved by finding the first k eigenvectors of a certain symmetric matrix, which is I minus the weights transpose times I minus the weights, something like that. And so these both are easy optimization problems. And the only parameter you have to fix is k in the KNN part. Anything else about this? Yes, okay. And okay, the embedding dimension can be estimated by a reciprocal cost function. That is what I was talking about before. So you take the weight, you take your points downstairs, the low dimensional ones. You find the best weights that write every point as a combination of the nearby points, and you bring the weights back on the manifold, and you see how much you get it wrong. And this gives you a cost function which you have to minimize to find the embedding dimension. So you just, obviously, you don't minimize it, you just check it for every embedding dimension, which is easier than minimizing. The algorithm scales well with data dimension and is incremental in the embedding dimension. So if you calculated everything from dimension k, to go to dimension k plus 1, you just need to add one step. You don't have to start back from the beginning. So it's quite, I mean, you just have to calculate one more eigenvector because everything else remains the same. So the only point which depends on the embedding dimension is the last, the step 3. So you just have to end, it's incremental. So you calculate the first k eigenvectors, you need the next one, ordered in terms of their eigenvalues. Okay, now I think the last algorithm, LTSA, local tangent space alignment, which is an intuitive idea. I mean, you could, actually is something one could come up without knowing much. Is a sort of local linear embedding, but not really. So you compute, I won't be going into depth in this part. You compute just the tangent space at each point of your data set. I mean, you use the neighborhood, the graph neighborhood, to compute the tangent space at that point. So what you have? You have an affine approximation of your space near the point. Then you calculate the tangent space at another point, and you have another affine approximation of your point. Now you want to glue them together. So you want to find what? An affine change of coordinates that glues the tangent spaces together. So that sort of unrolls your manifold. If you do that everywhere, you get a global parameterization. Now, the idea is easier than the others. The algorithm is much more difficult, really in terms like of linear algebra. But the ideal workflow is the following. You compute a KNN graph. You estimate the k-dimensional tangent space at each point using the neighborhood points. And you find this affine change of coordinates that flattens out all the tangent spaces. You get what is called an alignment matrix, collecting all these affine changes of coordinates, and you compute a global parameterization of your manifold. So this gives you, in the end, if it exists, a global parameterization of your manifolds. So it takes your manifold and unfolds it down on some RK. The nice thing is that this actually gives you an approximation for the Jacobian of the parameterization. So you can actually pull back things from the manifold to the parameterization because you have approximations of the Jacobian map. So for example, you can take the metric on your manifold and pull it back on the parameterization. So you have your RK that parameterizes your manifold, and you can define on RK the metric that it inherits from the original manifold. but it's quite, I mean, most of the work here is linear algebra, not differential geometry. And I think this is all for this first part on manifold learning, or the other name of this subject usually is non-linear dimensionality reduction, referring to the fact that linear dimensionality reductions are the PCA and SVD and MDC, all three letters names. And I think that's enough.